Hello, in this video I want to show you this really curious and unique old Soviet era plasma display called Электроника МС6205. I'll do all these things listed here, starting from overview. Those displays were used in CNC machines like these. Those machines was general purpose and they were capable enough of running something like 3D printer. And a curious thing about them that they used punch tape to enter G-code. So here is the punch tape reader. How cool is that? Also there was this computer that apparently can run BASIC. And these money counters also used display like that. Here's the unit that I got for $100 in very good condition, still sealed, made in 1987, serial number 3838. Let's power it up. Apparently it draws about 10 watts, and the indicator itself is a neon filled vacuum tube, contains 10,000 pixels, about 100 by 100 resolution. Here is how it looks up close. 1 pixel is weird, but it's fine. It works as usual. Here how it looks lit. Now let's get it to work. First I made it its own power supply. It requires 12 volts and 5 volts power supply. Then I figured what connector pins do. Like this one enables display, and these two can switch between pages. It can hold up to 4 pages full of text. Yeah, here I made a sketch that outputs every character in sequence, so I can map those from 0 to 127. I just write those down so I can know which numbers does what symbol. Here's the connector. It's a Soviet metric 2.5mm grid, but I'm using Imperial 2.54mm grid. They are not exactly matching, but there are like special spacing so they could fit. No idea why Imperial does like uneven numbers so much. That's weird. Here how power supply look like, and I'm using ESP32S3 as a controller. And here's the pin out of the connector and character table that I figured out. Okay, knowing all this, we can use it as a typewriter. Here I'm typing basic text for testing. Obviously it can output Cyrillic. No surprises here. Yep, subscribe to my channel. Now, this would be too easy. Let's open it up and see what's inside. So there are 5 boards. First board apparently contains some logic. Second board also contains logic, big memory chip and high voltage generator. This is how it looks up close. Okay, third board also contains some logic. And the whole thing can open like a book, except bottom 2 layers, because they are permanently... You can get to those because there are those ribbon cables that are looking like this. I don't want to even touch them, but they still works. That's fine. Okay, here's the fourth board, not very populated. And here's the last one, the most populated. I figured what this board do, and to put it simple, there is logic part and there is driver part. Here I want to look what's going on between those parts, between logic and driver. So maybe we can control the driver. Okay, There are several lines. First 8 lines are clearly sequential binary code, and that would be column selection. This pin does nothing because it's display enable when it's low. This is plus 5 volts and ground, extremely noisy, but within spec, so it's not a problem. Next 7 lines are random data, that would be pixel data. And this last line is very curious because it's 10 short pulses. That would be latch and clock. And last one is high voltage line, and it's interrupted. When we line up the interaction with those 10 strobes, they synchronized. So strobing going on when display is off. Since there are 10 pulses and 7 bits, we can assume that display has 10 rows. 10 rows of symbols, right? Each symbol has a height of 7 pixels. So those 7 bits would represent 7 pixels of one column of a symbol on each line. Now I'm checking the bottom part. No surprises there. They're mostly column and rows. Some are stuck lit. Some rows are stuck lit. Some are dead. And all columns are addressed. They have equal space in pulses. So here's the result. Here I'm confirming that I can indeed disable stuck on rows, and I can enable dead rows. So I can control them, right? Here's the perfect place for a board. Fits extremely well, there's enough space from both sides. I soldered these stuck on rows to this board using connectors. And for the other side too. Those are all dead rows except last one. Yeah, then I need to make keys for that. Here's how row key looks like. It's actually inverted, so when input is high, it acts like a voltage divider and outputs about 100 volts, which is not enough to lead the row, but provides some sustained voltage. And when the input is low, current goes through pull-up resistor, and row leads. There are rows that are stuck lit, and they have only pull-up resistor, and these parts are missing, so I had to add those. For dead rows it's even worse because they're initially not connected anywhere, so I had to add all these missing parts. And I also add this pull-up resistor, so when there is no input, both dead and lit rows act as usual. Dead stay dead, lit stay lit. Yeah, using scheme like this, resistors are running hot, but within spec those could heat up to 100 degrees with no problem. Also this fat one is cooking for some reason. Here I'm confirming that I indeed can control uncontrolled rows with my keys, same on the other side. Now here I fully interrupted connection between logic and driver and use those connectors for now as a bypass. Also I had to interrupt this line which controls strobe on high voltage. Here's the part that controls high voltage. It's inverted, so short pulses at the input, wide inverted pulses on the output. And I don't know why, but so it's like to double stack transistors like this. Okay, having all this, I can run this display without those weird lines that in my opinion is very ugly. But the thing is, this sort of display, which is DC plasma display, is very unstable unless there are certain amount of pixels lit, which is about 10% of pixels, and preferably they should be like in a sequence, in a row. So as you can see, there is a lot of flickering without those sustaining rows, and it becomes unstable. So those rows were put there for a reason. I will skip quite a bit in here. Anyway, this is the final, how the final driver looks like. Those are magic noodles, don't worry about it. Yeah, actually the idea was to preserve all logic, so here I interrupted the line between logic and original driver with my shift registers using multiplexers. Here's the final hardware, everything made on connectors. Actually, I didn't trace which wire goes where from those shift registers, so I had to do it in software. Here I'm passing data through display. This is how it works. This is same but with strobe. Here's the fast version. I needed to figure out pixels ordering. This is supposed to be a chess pattern. I figured it after a while. Yeah. Now at this point I can control every pixel individually, so I can output graphics like this. Then I made a simple application for capturing my screen, do some basic image preprocessing like exposure, brightness, contrast, whatever, and send this image in 8-bit format to a controller. Here's how it looks. And if I can send image, I can send video. Frames going one by one. You can see here flickering because the core is busy processing the frame. To prevent this from happening, I assign tasks like this. So core 0 does serial preprocess and tethering or scramble, and core 1 has one job to do: sweep the display. Okay, having that fixed, I can stream any video. Here is some example footage. Also, I want to show you that the old hardware and its text capabilities are preserved, and I can switch between modes pressing that button. Also, I can do things that Soviet people never imagined, like streaming virtual reality or AI videos.
Take the ticket. Busy here. Come on, take the ticket. Take it. Take the ticket.
I need this, right?
I remember your face.
Marvin. Marvin! I'd knock that shit off if I was you.
Nah, you mother.
Yeah, here I must say what could be done better. So right now I'm doing pure bit bang on this display through MCU cores, which is their own approach, but for now I don't want to redo it. But if I were to start from scratch, I would use ESP32 built-in DMA controller, which is like a small graphics card that can push bits from memory directly to display using not 1 but 16 or 32 data lines. And right now display can output about 50 to 60 frames per second, but if I would use DMA, it could output like 10,000 frames, and shades of grades would be so much better. Here I even tried that mode, but really I don't want to redo graphics. Anyway, yeah, I hope you enjoyed. Leave comments, see you around.